Hello viewers, today we are going to discuss about increasing and decreasing functions. Viewers, increasing and decreasing functions is an application of derivatives. With the help of differentiation, or we can say with the help of the process of differentiation, we can decide whether a function say y equal to fx is increasing or decreasing or neither increasing nor decreasing. So viewers, let us start our topic. Clear? So before explaining what are the rules to decide whether a function is increasing or decreasing, let us take a simple example, that is, say y equal to fx is equal to x square. Clear? And this is an parabola, and this represents a quadratic function. This represents a quadratic function, and here the domain is the set of all real numbers, while the range is the set of all positive real numbers. Clear? Now if we plot the graph of this function, then we see that we have a parabola like this. Clear? Now if we analyze the graph, and here we have -1, -2, -3, -4, and here we have 1, 2, 3, 4, 5, and so on. Now we take two cases. Case 1. Now if we approach from this side, that is, if we approach from left towards 0, we see that the graph decreases. Clear? The graph decreases. And if we take or if we proceed from right, and if we proceed from right, that is, if we take the points from 0 towards this side, then we see that the graph increases. Clear? So here's we see that as we move from left to right, we see that the height of this graph, what is the height? Say this is the height. Clear? So this is the height. See? So the height decreases. The height decreases. And if we move from left to right, as we move from left to right, the height of the graph increases. See? This is the height of the graph. Okay? So in this portion, the height of the graph decreases, and here it increases. Clear? So we can say that as we move from left to right along the graph, the height of the graph continuously increases. Clear? And the function is said to be increasing for x greater than 0. Clear? If we move from point x equal to 0 towards right, we see that the height of the graph increases, and for x greater than 0 the graph is said to be an increasing graph. Clear? Now similarly, we observe that if we move from left to right, that is from this side towards 0, we see that the height of the graph continuously decreases, because see, these are the heights and it continuously decreases for x less than 0. Clear? And this is the point x equal to 0. So in this portion, that is from say if I take this point A and this point O, so when we proceed from A to O or 0, here this is 0, so we see that the graph decreases. Clear? The height of the graph decreases. So this is the decreasing function from A to O. Now if we move from O to the right, then we see that if it is B, and if we move from O to B, we see that the height increases, and this is the increasing graph for x greater than 0. Clear? So this is the notion of increasing and decreasing function. Clear? In terms of graph. Clear? Let me take one more example here, and let us take one more graph. Clear? Suppose we have a graph like this. See, this is the graph. Now we see that if this is point A and this is point B, and if this is A and this is B, we see that the height of the graph continuously increases. Okay? Say if this is point x1, this is point x2, this is point x3, and so on, we see that if this is the function y equal to fx, then fx1 is less than fx2 for x1 less than x2. Similarly, fx2 is less than fx3 for x2 less than x3. So this is how we derive the meaning of increasing and decreasing functions. So the height of the graph increases continuously. So this is an increasing function. Now let us take one more graph, and if we take the graph as like this, and if say this is point A and this is point B, then we see that as we move from A to B, the height of the graph decreases continuously. Clear? Say if this point is x1, this point is x2, this is x3, and so on, and if say this is point B, and say this is point B, this is point A and this is point B. Okay, so we see that x1 is less than x2, x1 is less than x2, and fx1 is greater than fx2. Okay, so here this represents a decreasing function, and here we have the increasing function. Clear? So here's let us take one more graph here, and suppose the graph of a function is like this. Say this is the graph. Now we see that from our knowledge of functions, we see that at each point, if we take the points x1, x2, x3 and so on, then we see that the height of this graph remains the same. Clear? So this function represents a constant function. Clear? Now let us take the formal definition of increasing and decreasing functions. Now viewers, let us take the formal definition of increasing and decreasing functions. Suppose I be an interval which is contained in the domain of a real valued function f. Clear? That is, let the domain of the function say y equal to fx be d. Clear? And I be any interval which is a subset of this domain d. Clear? Now this function fx is said to be an increasing function, if now this function fx is said to be an increasing function on this interval I, where I maybe we can take I as this interval. Clear? So it is increasing function if x1, as I have just discussed the graph of increasing function, that if for x1 less than x2 in I implies fx1 is less than or equal to fx2. Clear? So for all x1, x2 belonging to this interval I. Clear? So this is said to be an increasing function if this condition holds. Clear? And the function is said to be strictly increasing. If x1 is less than x2 in I implies that fx1 is less than fx2, and this is also for all x1, x2 belonging to I. Clear? Now let us understand the graphical representation of this definition. Okay? Suppose we have the graph of a function, say this is the graph of the function. Now this is known as an increasing function. Okay? Because it satisfies our this definition. Clear? So we can write it like this, or we can draw it like this. So this is an increasing function. Why? Because for x1 less than x2, let us take this point as x1 and say this point is x2. Now obviously x2 is greater than x1. x2 is greater than x1. So this implies, and this is the, say this is the interval a and b. Okay, so x1 is less than x2, so obviously this height fx2 is greater than this fx1. Okay, so this height is fx1 and this height is fx2. Clear? And x1 is less than x2. So x1 less than x2 implies fx1 is less than fx2. So therefore this is called an increasing function. Okay, now here we have the equality sign. So what does it mean? So it means that if a function is like this, say this and this and this, okay, then for any value of or for some value of x1 and x2, we can have fx1 is equal to fx2. Clear? For instance, here if we have x1 here and we have x2 here, now this is an increasing function. Clear? Now although x1 is less than x2, but this implies that fx1 may be equal to fx2 here. This is an increasing function. Okay, so this is how we explain the definition of increasing function. Okay, now let us take one more example here. Now if we have a graph like this, say if we have a graph like this, say the graph is like this. Now we see that if this is point A and this is point B here, and if we take any 2 points x1 and x2, then we see that x1 is less than x2 implies that this fx2 is greater than fx1 for all x1 x2 belonging to I. Clear? And where I is this interval. Clear? So we see that if we take any two values, then the height of this graph always increases. Clear? For any 2 points. So if I take, say this is x3, then x3 is greater than, say, x2, then this implies that fx3 is obviously greater than this is x3 here, and fx3 is greater than fx2. Clear? So this is called a strictly increasing function. This is called a strictly increasing function. So in strictly increasing function, we do not have the equality sign here. Clear? For any 2 points, say x1 and x2, we strictly have this inequality. Clear? So let us now consider the definition of decreasing function. Now viewers, again we have a function y equal to fx, and suppose I is any interval which is a subset of the domain of this function, and now this function fx is said to be a decreasing function if x1 is less than x2 belongs to in I, implies that fx1 is greater than or equal to fx2 for all x1 x2 belonging to this interval I, then this function is said to be a decreasing function. Okay, and if x1 is less than x2 in I, implies fx1 is greater than, here we do not have the equality sign, so fx1 is greater than fx2 for all x1 x2 belonging to I, then in this case the function is said to be strictly decreasing function. Clear? This is called strictly decreasing function. Clear? Now let us take a graph of a decreasing function. So let us take say this graph here. Okay, now suppose we have a function like this, say this. Clear? Now this function is said to be a decreasing function. Why? Because if I take 2 points on this graph, then we see that if I take, say this is x1 and say this is x2. Clear? This is x2. Now obviously x2 is greater than x1. Okay, x2 is greater than x1. So this implies that the height fx1, this fx1 is greater than fx2. So this is how we explain this definition. But if we have a point here, say x3 and say x4, then we see that x4 is greater than x3. x4 is x of 4 is greater than x3, implies fx3 is equal to fx4. So this explains the equality sign here. Clear? So in this case this function is said to be decreasing function, because when we have taken these 2 points, x1 is less than x2, and this implies that fx1 is greater than fx2. So this is decreasing function, and to incorporate this equality sign, if we take 2 points x3 and x4 in this part of the function, because this is a straight line here, or the function is said to be a constant function here. So we have x4, although x4 is greater than x3, but the ordinates at these 2 points are equal. Clear? So in this inequality we have considered both the cases. Clear? So this is a decreasing function. Clear? Now let us take the case of strictly decreasing function. Strictly decreasing function. So for strictly decreasing function, we have the inequality sign. We do not have the equality sign. So let us take the graph. Clear? So here we have the graph of the function like this. Clear? Now this is the point A, and here we have point B, and let us take 2 points here, say this is x1 and this is x2. So here's obviously x2 is greater than x1 here. Now the ordinate fx1 is greater than fx2. If I take this point as A and this point as P, this is point B, this is point Q, so AP is equal to fx1 and BQ is equal to fx2. So therefore fx1 is greater than fx2, or AP, this height AP is greater than BQ. Okay? So this is how we explain the definition of decreasing function and strictly decreasing function. Okay? So here at all points, if we take any 2 points in this graph, then we will always have a strict inequality sign here. Okay? We cannot have the equality sign here for any 2 points x1 and x2 belonging to this interval I. Clear? Now viewers, so far we have discussed the concept of increasing and decreasing function in terms of the graphical representation. Clear? Now let us explain, or let us have the application of derivative in understanding the concept of increasing and decreasing functions. Clear? So let us introduce here the concept of derivative to find whether a function is increasing or decreasing or neither increasing nor decreasing. So let y equal to fx be a continuous function, is a continuous function on some interval I. This is the interval I, and let us take this interval I as a comma b. This is the closed interval, and this function is continuous in this closed interval, and this function is differentiable in the open interval a comma b. Clear? Then now we are going to establish the condition for a function to be strictly increasing or strictly decreasing, or the function is a constant function. Clear? So then f is said to be, and f is said to be strictly increasing, said to be strictly increasing on this interval I, which is AB, if the derivative of f, that is f prime of x, is greater than 0 for all x belonging to this open interval a comma b. So here's always remember, we can write it as dy over dx is greater than 0. So if the derivative at each x belonging to this open interval a comma b is positive, or it is greater than 0, then the function is said to be strictly increasing. So the derivative has to be positive here. Clear? So the derivative has to be positive. It means the slope of the tangent at that point x should be positive. Clear? Now f is said to be, if f is said to be strictly decreasing on this closed interval a comma b if the derivative is less than 0 for all x belonging to a comma b. So what does it mean? It means that if the derivative is less than 0, if the derivative is less than 0 or the derivative is negative, then the function is said to be strictly decreasing function. Clear? And the last case is f is said to be a constant function, in a comma b if the derivative is equal to 0 for all x belonging to a comma b. So it means here we have the derivative is 0 or the derivative is equal to 0. So if the derivative of the function is 0 or it vanishes for each x belonging to the open interval a comma b, then the function is said to be a constant function, because in that case the tangent becomes parallel to x-axis. Clear? So viewers, here I am once again revising what we have discussed so far. So we have a function y equal to fx which is continuous in this interval, closed interval a comma b, and it is differentiable in open interval a comma b. Now then f is said to be strictly increasing. It is strictly increasing on this interval if the derivative is positive. F prime of x is greater than 0 for all x belonging to a comma b. And f is said to be strictly decreasing on this closed interval a comma b if f prime of x is less than 0 or the derivative is negative, then it is said to be strictly decreasing. And f is said to be a constant function if the derivative is 0. It means the tangent is parallel to x-axis. Clear? So viewers, this is all about increasing and decreasing functions, and these are the rules how to claim whether a function is increasing or decreasing. Now viewers, we'll solve some problems and we'll find the intervals in which a particular function is increasing or decreasing or neither increasing nor decreasing. Clear? Now viewers, we have just discussed that a function y equal to fx, if it is defined on an interval a comma b, which is a subset of its domain, then this function fx is said to be strictly increasing if the derivative is greater than 0, right? Or the derivative dy by dx is greater than 0. So this we have discussed just now, and with the help of this graph we'll try to explain this result. Clear? So here we have a graph of a function ab which is an strictly increasing function. Clear? Now let us take a point here, clear, and draw a tangent at this point, clear. So we'll draw a tangent here. So this is the tangent, clear. So viewers, here we have the tangent, and say this point is C, clear. So this ordinate is f of C here, and say this is angle theta, clear. Now this point is say P, then the slope of the tangent at the point P, P is given by the derivative of y with respect to x at x is equal to c, or we can write it as f prime of c. So we see that the slope is also given by m is equal to tan theta, and theta is acute here, acute angle. Here theta is acute angle, and therefore it lies in the first quadrant. So therefore tan theta is positive in first quadrant. So m is positive. M is positive. And what is m? M is f prime of c. So m is positive means m is greater than 0. So f prime of c is greater than 0. So this is how we get this result. Clear? So if a function is strictly increasing, then the derivative of that function at any point on the graph of that function is always greater than 0. As we have seen in this case, we have taken a point C here. So we see that the slope of this tangent, which represents the derivative of y with respect to x, is greater than 0. Clear? Now viewers, let us take a look at this graph, and we have y is equal to fx be the graph of this function, and this is defined in this interval a comma b, and say this is a and this is b. Now viewers, we see that this graph represents a decreasing function or a strictly decreasing function. So therefore we have just discussed that y is strictly decreasing function. Y is strictly decreasing function if the derivative of f is less than 0, or dy over dx is less than 0 for all x belonging to a comma b. Clear? So let us interpret this result with the help of this graph. Okay. Now let us take a point C between A and B. Clear? This is the point C, and let us draw a tangent at this point. At this point. So this is the tangent. Okay, this is the tangent. So this is the tangent at this point C. Now here's this is the angle theta. Now we see that the slope of this tangent, because this is a strictly decreasing function, and the slope of this tangent is given by m is equal to tan theta, and theta is obtuse angle. This is obtuse angle, and it lies in the second quadrant, and in second quadrant tan theta is less than 0. Clear? So tan theta is negative in second quadrant. So m is less than 0. And what is m? M is the derivative of f. Clear? And this is dy over dx. So the slope of the tangent at point C is represented by f prime of C. Clear? So f prime of C is less than 0 because m is the derivative of y with respect to x at this point C. Clear? So this is how we get the expression that for strictly decreasing functions the derivative of the function is less than 0. Clear? So this is strictly decreasing function, and we have the slope of the tangent as negative. Clear? Now viewers, let us consider the third case. So if y is equal to fx be the function and defined in the interval a comma b, and if the graph of the function is like this, this is the graph of the function, because here this function fx is constant function. Fx is a constant function. So if fx is constant function, say fx is equal to say p. Clear? So obviously the derivative is 0 because the derivative of a constant function is 0. So the derivative is 0. It implies that the slope of the tangent is 0, or the tangent is parallel to x-axis. Clear? So here we have the case. If we have this function which is defined in the interval a comma b, and it is a constant function, then obviously the derivative is 0 here. So this is the ordinate for all points. For example, if we have x1, here we have x2, we have x3, and so on, and x1, x2, x3 all belongs to this interval a comma b. So whereas we have f prime of x is 0, means the derivative is 0. The derivative is 0. It means f prime of x1 is 0, f prime of x2 is 0, f prime of x3 is 0. So at all points the slope is 0. It means the function, the slope of the function is 0, and the tangent at all these points is parallel to x-axis. Clear? So this represents a constant function. So when f prime of x is 0, the function represents a constant function. Clear? Now viewers, we have discussed all the concepts related to increasing and decreasing functions, and now we are in a position to solve some elementary problems or some conceptual problems. So the first one is, show that the function fx is equal to 4x plus 5 is strictly increasing function on the set of real numbers. Clear? So here's what we have just discussed, that if we have a function fx, y equal to fx, then this function y equal to fx is strictly increasing if the derivative of f is greater than 0 for all x belonging to the given interval. Clear? So let us apply this rule to this question. So here we have the derivative of f is 4. We have 4. Clear? Because the derivative of x is 1 and the derivative of 5 is 0, so we have 4, and 4 is greater than 0 for all x belonging to the set of real numbers. So therefore f prime of x is greater than 0 for all x belonging to R. Hence fx given by 4x plus 5 is strictly increasing on R. Clear? Now viewers, at the same time, if we have a function like this, say instead of fx equal to 4x plus 5, if we have minus 4x plus 5, then what we will do? Then again we'll find the derivative here. F prime of x is given by minus 4. The derivative of x is 1. This is 0, so we have minus 4, and this is less than 0 for all x belonging to R. Clear? So therefore in this case f prime of x is less than 0, because f prime of x is minus 4, which is less than 0. So the derivative is less than 0 for all x belonging to R. So therefore this function fx is equal to minus 4x plus 5 is strictly decreasing on the set of real numbers. Clear? Now viewers, we have this exponential function here. Show that the function fx is equal to e raised to 2x is strictly increasing on R. So we have f of x is equal to e raised to 2x. Now we find the derivative. So we have e raised to 2x times 2. So this is 2 e raised to 2x. Now viewers, from this expression we see that for all x belonging to R, the first derivative, the f dash x, is greater than 0, because whatever be the value of x, the first derivative is always greater than 0. So therefore fx is equal to e raised to 2x is strictly increasing on R. See, if we have x equal to 0, we have f prime of 0 is 2 times e raised to 0, which is 2, which is greater than 0. If we have x is 1, so f prime of 1 is 2 times e raised to 2 times of 1. So we have 2e square here, and this is also greater than 0. Similarly, if we have x is equal to minus 1, then f prime of minus 1 is 2 times of e raised to minus 2, because here we substitute x equal to minus 1, and this can be written as 2 divided by e square, and which is greater than 0. So in all cases, whether it is 0 or a positive number or a negative number, the first derivative f dash x is always greater than 0 for all x belonging to R. Clear? So therefore fx is equal to e raised to 2x is strictly increasing on R. Clear? Now viewers, here we have the problem proof that the logarithmic function is strictly increasing on this interval. So here we have the logarithmic function fx is equal to log of x. Now we find the derivative here. So we have 1 over x, because the derivative of log x is 1 over x. Now viewers, here we have the derivative of this log function equal to 1 over x. And we see that if we take this interval 0 to infinity, that is we have here 0 and here we have infinity. So if we take this interval, then we see that 1 over x is always greater than 0, because we have here all positive real numbers. Now here we can also say that if x belongs to 0 to infinity, then 1 over x is always greater than 0, and which implies that f prime of x is greater than 0. So therefore this logarithmic function is strictly increasing on 0 to infinity. Clear? Because here we have if x belongs to this interval which is given here, then x is always positive. X is always positive. So x is always positive in the interval 0 to infinity. So therefore 1 over x is always positive, and 1 upon x is equal to the derivative of f. So the derivative of f is greater than 0, and this is the condition for a function to be increasing. Clear? Now viewers, let us consider this problem. Here we have to prove that the function fx is equal to x cube minus 3x square plus 3x minus 100 is increasing in R. Clear? Now let us find the derivative of this function fx, and the derivative is 3x square minus 6x plus 3. The derivative of 100 is 0 because it is a constant function. The derivative of x is 1, so this is 3 times of 1, this is 3. The derivative of x square is 2x, so this is minus x 6x, and the derivative of x cube is 3x square. Now yes, this can be written as 3 times of we take 3 common here, x square minus 2x, this is plus 1. Clear? Now this can be written as x minus 1 whole square. Now here we see that the derivative is given by 3 times x minus 1 whole square. Now this quantity is always positive. See, prove that the function is increasing in R. Clear? So for x equal to 0, for x equal to 0, the derivative is for x equal to 1, I correct it, this is for x equal to 1. So for x equal to 1, f prime of 1 is 3 times of 1 minus 1 square. This is 3 times of 0 square, which is equal to 0. So f prime of 1 is 0, and for other values of x, this quantity, that is for other values of x, this quantity is always positive. So therefore we see that the f prime of x is always greater than or equal to 0. Whereas this is a very conceptual problem here. See, we have a function here, this is a cubic function, and we have to prove that this function is increasing in the set of real numbers. So we have obtained the derivative as 3 times x minus 1 whole square. Now for x equal to 1, the derivative vanishes, it is 0. It means at x equal to 1, the tangent, the slope of the tangent is 0, or the tangent is parallel to x-axis. Clear? And for other values of x which belongs to the set of real numbers, f prime of x is greater than 0. So if we include the entire set of real numbers, that is including 1 also here, or we have just taken x equal to 1 as a special case here. Otherwise we can directly say that for the set of real numbers f prime of x, that is the derivative, is greater than or equal to 0. So this is the condition for a function to be increasing. Clear? So hence this function fx is increasing in the set of real numbers.